Okay, so hello and welcome everyone to the ninth week of interactive live sessions for the course Computational Fluid Dynamics for Incompressible Flows. As we already know, this course is being offered by NPTEL. It's being instructed by Professor Amaresh Dalal from the Department of Mechanical Engineering at IIT Guwahati. My name is Debjit. I'm the TA for this course, and like every other week, we shall be solving some problems together. But before that, so up until now, we have been dipping our toes into the world of computational fluid dynamics. We learned how to, classify different partial differential equations and a little bit of different schemes of how to solve them. We also looked at, concepts of stability and other ways of modeling it, like instead of solving the Navier-Stokes equations, how can we convert it into stream function vorticity formulation and solve it. But this week, week 9, is where we really delved into how to actually solve Navier-Stokes equations, because they are generally solved using finite volume method. That's the more popular method, and in the later half of this course, we will learn that. But so far, our learning of finite difference method also hasn't gone to waste. We use it to solve Navier-Stokes equations using a particular method known as the marker and cell method, which we learned during this week. So, uh, without any further ado, let's jump into the questions. So, the first question asks us that what is the primary difference between a staggered grid and a co-located grid? Is it option A, the location of the grid points relative to the fluid flow? Is it option B, the resolution of the grid in different regions of the computational domain? Is it option C, the type of interpolation used to calculate the values of fluid variables? Or is it option D, the number of dimensions used to represent the computational domain? What is the main difference between a staggered grid and a co-located grid? Okay, so let's take a look at the answers. It is option A, the location of the grid points relative to the fluid flow. So basically, this is what we learned, right? Right. So co-located grid is something like this, where in each cell, in the cell center, all the values, the pressure, velocity, and even if you are solving for, you know, temperature and things like that, they are all located in the same space, same location in space. That's why it's called a co-located grid. Whereas in a staggered grid, we save the pressure and other scalars in the cell center, whereas we shift the velocity vectors in a different direction. So u would be shifted to the side, whereas the v velocity, that is shifted up top. So the location where of these grid points relative to the fluid flow are different. So that's why it should be option A, the location of grid points relative to the fluid flow. Alright, so this was an easy one. Let's move along. Move on to question number 2, which is asking us what are the number of cells for U and V individually, respectively, if P pressure has m cross n cells. Is it option A, m cross n for both u and v, that is, there's no difference, both have the same number of cells as p does? Uh, Option B says m plus 1 cross n for u and m cross n plus 1 for v. And option C says m cross n plus 1 for u and n plus 1 cross n for v. And option D says m plus 1 cross n plus 1 for both u and v. Again, it's the same for both u and v, but one more each in both direction than p. And this is in the context of staggered grid. Okay, so let's take a look at the solution. There's actually option B, m plus 1 cross n for u and m cross n plus 1 for v. So let's take a simple example. We will use a 4 cross 4 grid for p. Right. So let's use red dots to denote p. So we have 1, 2, 3, 4 cross 4, total 16 values where p is stored. So m equals n equals 4 for pressure, right? Now let's try to draw u. I'll change the color of my pen. Let's take green, for example. So u would be on the vertical faces. So 3 interior into 4. And there will be one each at the boundary as well. So at the boundary, there will be 3 here, and in the bottom boundary also, there will be 3 over here. Sorry, not like this. Okay, I wiped off most of it. Let me draw again. And in these boundaries, the vertical faces there will also have values of u stored in them, and they will be determined by the boundary conditions. So for u, if you take a count now, on the right hand side there is 1, 2, 3, 4, and 5. So m plus 1 in the x direction, and in the y direction it's the same as the number of points for pressure, so N. Similarly, for vertical velocity or y velocity v, there will again be 1, 2, and 3 interior points and 2 boundary points. So 5 in the y direction, and it will be repeated 4 times. So for v in the x direction, there are 4. So it's the same as p, so m. But in the y direction, there is 1 extra. So n plus 1 grid points. So the size of the matrices where you store these values of u, v, and p, they will be of different sizes. So this is one of the disadvantages of the staggered grid. Maintaining proper data structure is a bit difficult, but then again, it has other benefits which outweighs these problems. Okay, any questions on this? If not, let's move along. We'll move on to question number 3, which is a match the following type of question, and it's regarding staggered grids once again. So if you look at this carefully, we have variables u, v, and p in the left column, whereas in the right column we have the different locations where these variables can be stored. So which are the cell centers, vertical faces, and horizontal faces. So if a cell is like this is the cell center I. The vertical face, what I mean by a vertical face is this one, 2, and a horizontal face is this one, 3. These are both 3, by the way, the top and bottom one. So you have to match which variable is stored where, and there are different combinations given in the options below. You have to pick out which one matches your solution. So is it option A, A1, B2, C3? Is it option B, A3, B1, C2? Is it option C, A2, B3, C1? Or is it option D, A3, B2, and C1? So try to match them first. Then once you get an answer, try to find if that option, that solution exists within the options given. Then you can either type in the chat box or you can unmute and answer, whichever way you feel comfortable. There's no hurry, take your time and figure out the correct solution to this question. Alright, let's take a look at the answer. It is A3B2C1. So I think there was a mistake in the previous slide. So this is what I mean. So this is the cell center, and these are the horizontal faces. Actually, no, the horizontal faces should be the other way around. So, correctly, this is one, these are vertical faces, and these are horizontal faces. And as we know, U is stored in, sorry, V is stored in 3. So, V should be 3, U should be 2, that is over here in the vertical faces, and P obviously in the cell centers. So it shouldn't be D, it should be A2, B3, and C1. That is, C should be the correct answer. All right, let's move along to the next question. This is option question 4. This is asking us which of the following is a limitation of the staggered grid? Is it option A, that it is only suitable for incompressible flow simulations? Is it option B, that it can only be used for 2D flow simulations? Is it option C, that it is less accurate than other numerical methods for simulating fluid flow? Or is it option D, that it requires difficult bookkeeping? Which of the following is a limitation or the disadvantage of using a staggered grid? Is it that option A, it is only suitable for incompressible flow simulations? Is it option B, that it can only be used for two-dimensional flow simulations? Is it option C, that it is less accurate comparatively than other numerical methods? Or is it option D, that it requires difficult bookkeeping? Let's take a look at the solution. It's actually option D, that it requires difficult bookkeeping, because as we saw that the variables P, U, and V, they have different sized matrices, plus you know plus on top of that their locations are also different. So let's say these among these 3 points A, B, and C, if I want to know the location of these points in space, so let's say I want to know what is the x and y coordinates of A versus the x and y coordinates of B versus the x and y coordinates of C. Uh, these three won't be the same. They would not be equal to each other. They would, so there has to be some more uh, you know ways to store the values of x and y coordinates of uh, each point where a different variable is stored. Now, if I have a perfectly structured grid, then it's fine. There should be some logic which will help me find that. But if we are using an unstructured grid, then in that case, it becomes very difficult. So in that case, you have to store these coordinate locations as well. So the main thing is the data structure, the way things are stored, and the bookkeeping in general becomes very difficult when you are using staggered grids. That's a big disadvantage of this. Otherwise, there are many other benefits which outweigh these problems. Anyway, let's keep moving. We'll move on to question number 5 now, which is asking which of the following is a limitation of the co-located grid. Is it once again that it is only suitable for incompressible flow simulations? Is it because it is less accurate due to the use of a coarser mesh than the one considered? Is it option C, that it produces spurious results in case of checkerboard velocity or pressure fields? or is it option D, that is both B and C? Let's take a look at the solutions. It is actually both B and C because both B and C are true. So it is indeed less accurate, and because of the use of a coarser mesh. So we saw that, if we have to find the velocity gradient dou u dou x, I end up doing something like ue minus uw divided by 2 delta x. So I am forced to take 2 points 2 delta x apart, whereas my mesh is delta x, of resolution delta x. So my mesh resolution becomes half because of the scheme being used in case of a collocated grid. And it also produces spurious results in case of checkerboard velocity or pressure fields, because we saw that pressure and velocity fields, they become decoupled when using collocated grids. So let's say if I have pressure field like this, which is 200, 100, 200, then again 100. So if I'm trying to find the pressure difference here at this point, or the pressure gradient here, I will, end up doing something like this. So if this is P, E, and W, so my pressure gradient would be calculated as PE minus PW by 2 delta x, which would give me 0 because both PE and PW are the same, right? So in this way, the velocity and pressure, they stop talking to each other, and that results in decoupling, and finally it gives us incorrect results. So both B and C are correct. That's why you have to choose option D, that is both B and C. All right. So let's take a look at the next question. Question 6, which is asking us the staggered grid can be used to overcome dash. You have to fill in the blank over there. So is it option A, decoupling of pressure and velocities, option B, coupling of pressure and velocities, option C, interpolation problems, or option D, boundedness problems? Question number 6 of today's session is a fill in the blank type of question, where the statement is that the staggered grid can be used to overcome blank. Now the options for filling the blank is option A, decoupling of pressure and velocities, option B, coupling of pressure and velocities, option C, interpolation problems, or option D, boundedness problems. Let's take a look at the solution. It is option A. As we discussed in the previous slide, the pressure and velocity gets decoupled in collocated grids, and that is overcome using a staggered grid. Alright, moving on. Moving on to question number 7. Which of these is not stored at the cell centers? So the keyword here is not stored at the cell centers in the staggered grid. Is it option A, density, option B, pressure, option C, temperature, or is it option D, none of the above? Which of these are not stored at the cell center in this diagram? Let's take a look at the solution. It's actually option D, none of the above, because all these three are what? They're all scalars, and all scalars are stored at the cell center in a staggered grid. So, which is why none of these are not stored. They are all stored in cell center. So, the correct answer to this question would have been option D, none of the above. I hope that's clear. Let's move along. We'll move on to question number D. the question number 8, sorry, which is asking us that in order to calculate drag and lift forces, which method is more suitable? Is it option A, the stream function vorticity approach, or is it option B, the primitive variable approach? The stream function vorticity approach uses two variables, omega, that is vorticity, and psi, that is the stream function. And the primitive variable approach tries to solve for the uh, the actual original primitive variables which show up in the Navier-Stokes equations, which are velocities and pressure, which are much more fundamental than vorticity and stream function, which are derived quantities. Let's take a look at the solution. It's actually option B, primitive variable approach, where you solve for u, v, and p. That's because of a certain reason. So let's say I have uh, an aerofoil like this of a weird shape, and there is a flow around it. So this is similar to an aeroplane wing while the airplane is in flight. So if we are interested in the aerodynamic forces on this, so basically we want to compute what is the drag force, which is parallel to the direction of flow, and as well as the lift force, which is in the perpendicular direction to the flow. So if you are interested in finding out these forces, the way to do that is to find the pressure distribution along the periphery of a given body. So there will be pressure at each different point due to the aerodynamics. So the way to find these forces is to know what the pressure is at each point, and then take an integral over it in the given direction to find the forces. So FL would basically be P dot di over the whole surface multiplied by some breadth and all that. So force into area, sorry, pressure into area gives me force, and that has to be uh, computed over the entire domain, and that gives me the different forces. So I need the pressure, and in the primitive variable approach, pressure is explicitly solved instead of the stream function vorticity approach, where we learned that we solve for psi and omega, and then finally we can find the pressure using a pressure Poisson equation, but it's not explicitly solved every time. So we have to keep going back and forth in order to get the pressure. So in case of an unsteady situation, we need the pressure at every time step. So in that case, the primitive variable approach is much more suitable. All right. So moving on, we move on to question number 9, which is asking us that in MAC algorithm, how is the pressure correction at the neighboring points calculated? Is it by option A, calculated by normal interpolation? Is it option B, calculated by weighted interpolation? Is it option C, solved using TDMA, that is tridiagonal matrix algorithm? Or is it option D, assumed to be 0? Okay, so we have a quick response in favor of option D, assumed to be 0. So let's take a look at the solution. It's indeed option D, assumed to be 0. So that is one of the tricks of the marker and cell algorithm, where the pressure correction is solved only at the point of interest and the neighboring points are ignored while calculation. But we do solve this whole thing iteratively until we finally arrive at the correct solution, which gives us convergence. So so that is what is done in the marker and cell algorithm, where the pressure correction at neighboring points are ignored. Okay, So moving on, we move on to the last question of today's session, which is asking us that in the marker and cell algorithm, the MAC algorithm, where does the pressure correction equation originate from? Is it option A, the continuity equation? Is it option B, the x momentum equation? Is it option C, the y momentum equation? Or is it option D, none of the above? Alright, once again we have a quick response in favor of option A, the continuity equation. Let's take a look at the solution. It is indeed the continuity equation. So uh, we find the nominal values u and v, u tilde and v tilde, and then in the continuity equation we plug those in, and these are all functions of the pressure correction terms. So finally, if we substitute those over here, we finally arrive at the pressure correction equation, which relates the pressure correction to the nominal values of u tilde and v tilde. And then the pressure correction equation is further simplified by ignoring the neighboring correction quantities and only keeping the pressure correction at the point of interest, and then solving it iteratively until we reach convergence, which is again uh, checked by checking the continuity equation. The residuals of the continuity equation should go below a certain tolerance where we can safely say that yeah, our solution has converged and we are happy with the numbers that we have arrived at. All right, so that's all for today. If you have any questions, you can ask now.
Yeah, actually, actually, there's some lecture part remaining. That's why I joined late. Uh, yeah, in the ninth week, so I need to collect some doubts. So that's why. So actually, the first thing is I will go like in the flow between parallel plate. The outlet conditions are told that gradient of u is 0 and gradient of v is also 0.
Yes.
So as liquid is coming, it will go out.
Hmm.
But if once that flow is fully developed, it will be a parabolic profile.
Yeah.
So in the middle, u is maximum. Then going towards the boundary, it is minimum.
Yeah.
Then the gradient in y direction,
Hmm.
gradient in x direction, okay, it is 0
Hmm.
because u in the middle is going to be after fully developed is going to be 0 because it is same.
Hmm.
But in y direction,
Hmm.
how it is, how the gradient is 0.
It's not zero. So outflow condition is towards the direction of the outflow. That is, only the x gradients are zero. The y gradients are not zero.
Okay, but okay, let me tell you like in which slide it is. Just a minute.
You can check, like if it is, if you see that somewhere that you know, in a case of a parallel plate, if it says that y gradient is also zero, then that's not correct.
Just a minute. Yeah. Can you please open V-Gate lecture 2?
Okay, hold on a second. So I'll stop sharing this.
Yeah.
A second. Can you see my screen? No, right?
No.
What about now?
Yeah, yeah. Now I.
So which week?
Week 8, lecture 2.
Week 8, lecture 2.
Notes.
Oh, right.
Right.
So, yeah. Which
Yeah.
page?
Next slide. Next slide. Further next. Okay. Yeah, you keep rolling. I will tell you where to stop. Yeah, here.
Hmm.
Yeah, in this, like the outlet condition, del u by del x is zero. That's okay, but okay, del v by del x is zero, not del y. I guess. Oh,
No, this will also be in the x direction. So, what's fully developed means that in the direction of the flow, it's not changing anymore. And anyway, V is like what everywhere zero in case of a parallel flow in a parallel plate, laminar flow in between parallel plates.
yeah, but it was told that as the flow is coming, it is going, but it is not going as the same because it is coming as this constant u from top to
Hmm.
bottom, but it's going out as a parabolic profile, like maximum in
So
between and
if
then.
you fix a y direction, y coordinate, then u is not changing in the x coordinate. That's what is meant by whatever is coming, the same is going. So let's say if you took two different cells, one exactly at the boundary and one layer of cells just before the boundary, then the velocities in both layers of cells will be the same, like at each y location.
Okay, in Y location, yeah, I understand. In Y location, it's same, but
Yeah,
in X, I mean, in once Y is fixed in X, it is not varying.
yeah.
Okay, okay, okay. Actually, I think that it is del V by del Y. Okay,
Uh,
okay, no, sorry. Yeah, and the next question is what is okay, this I think I have asked. What is primitive? Yeah, just now you're also explaining about the primitive approach.
mm,
Like so this vorticity stream function equation, it is not a primitive approach because we are going some derivative of u and v.
exactly. Some
And
derived quantities.
yeah, and this primitive approach, whenever we are the main variables in our equations are u, v, w, v, then this is called as primitive equation in
Yeah,
general. It is in general.
yeah. Because
Okay.
velocity you can see, pressure you can measure, but there is no device which can help you measure speed function at some point. You cannot measure
Okay.
vorticity at some point. If you see the velocity, then you can compute these quantities.
Okay, that's why it is called primitive
Yeah,
approach.
yeah.
Okay,
But
and why like it is a preference for solving the Navier-Stokes equation that we have already seen that this vorticity is a problem in there. And even I want to like I come across this thing in the last session. You have asked a question that if we go for 3D
mm,
using vorticity string function, then what is the problem you told is like I also agree with that
mm,
that the problem is that it is very complicated and we need tensors to solve it.
yeah,
But I also find one thing that even the stream function is defined only for 2D, not for 3D.
yeah.
So
There is a vague, like very vector definition of stream function in 3D. It doesn't. It's not that it doesn't exist. It does, but
mm,
it's more complicated and it doesn't really help us over here.
okay, so I like I mean to say like when in 3D stream function exists.
Yeah, it does. So
Okay,
there's a book on
actually at
advanced
one
fluid
point in
mechanics.
video,
Yeah,
actually at one point in video, sir told that stream function is defined only for
yeah, I
2D.
heard that. So for basic level courses and catering to the common audience, he may have told that. But
Mm-hmm.
there is a 3D version of stream function as well. Like,
Okay.
if you can see my screen, I'll Google it.
Yeah.
So in advanced fluid mechanics books, you will find this.
Yeah. 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 3D stream functions.
This is in 2D. Yeah, see Euler's equation in 3D. It has used psi in 3D is the string one.
Okay. Yeah. Yeah.
So there is a definition. I mean, you can check the on fluid mechanics by Kundu and Cohen. It's there.
Okay.
Anyway,
Okay. So, and the next thing is like, what is this non-conservative form of equation and conservative form of equations?
yeah. So that's the way we. That depends on the way we write our partial differential equation. Basically, the Navier-Stokes equations. So the convective term is written in what way? U dou u dou x plus v dou u dou y, right?
Yeah.
So in the, let's say for the x momentum equation. So the way I said it, that's the non-conservative form, and the conservative form would be to insert those multiplied u's and v's into the derivatives, and then talking about. There's a particular reason why we do that. So maybe once we have seen the lectures, I will make sure that we discuss this at some point
Which lecture?
later on. Like we will learn finite volume method the upcoming weeks. So their conservative and non-conservative forms will be discussed, I hope.
Okay, so this thing is discussed in the upcoming lectures.
Yeah, yeah.
Okay, okay. And then the next thing is, okay, yeah. So can you open week 9? Yeah, week 9. The first lecture.
First lecture.
Hmm. So this is okay. Next year. Next year. Yeah. Yeah. No, okay, for the next. Here. Can you expand? Yeah. Okay. So first of all, why this del y and del I mean delta x, delta y is one thing, del y and del x is another thing.
So in a
Like why?
structured grid, yeah, yeah, I understand that. So in a structured grid, they will be the same. If it is
Mhm.
unstructured, or if there is differences between the cell sizes, then these would be
Mhm.
different.
But still, then we take this when we interpolate the pressure at PE small e,
Hmm.
then still we can take the average even if it is not at the center. Bec-
Yeah,
Even though,
you can use weighted interpolation then. Like the one that is closer will have a
yeah, yeah,
greater
yeah.
weight, and the one that is further will
Okay,
have a
okay, okay.
lower weight.
Yeah, yeah, makes sense. Really makes sense. I understand. So based on the distance, basically, we can make this.
Exactly.
Yeah, yeah, yeah.
Exactly.
Okay. So, and the next thing is why we go for this small e. I mean, if I am at P,
Hmm.
capital P,
Hmm.
when I am writing del P by del X,
Hmm.
then why I go to small e and W? Why I don't go directly to capital E and W?
So you can
Because
directly make that jump. I mean, let's say earlier when we were doing central difference and all that, we went to this
Mhm.
directly. But here it's just to show the difference, since we already have a staggered grid sort of embedded on top. You can, so you take this dashed line, dashed cell around P, right?
This one is non-staggered actually. Like, but here this is for non-staggered
This is
staggered
for the
grid
grid,
we are
yeah.
writing.
But anyway, so the main point over here is that we're losing out on grid resolution. We are using a co-located grid. Like if we knew the values of P at small e and small w, then we could have gotten higher accuracy. But we are forced to take the
No,
values of.
my question is why we need this extra small n e the s w
Just to,
when we already had.
Yeah.
this capital N E W S, and we can write
We can
this.
go directly, but it's too, so we can compare with the staggered grid as well, because in the staggered grid we have it in that manner where there is a small e, small n.
Okay, so for comparison,
For
like to have a better, like similar approach in both the things.
exactly,
That's why
exactly,
we.
exactly.
Okay, can you go previous, like previous? Yeah, yeah. Okay, so that's why we have written just to make this. We can directly. Okay. Now this checkerboard pressure grid distribution, I understand this thing,
Hmm.
but the problem is like where we are going to have such kind of pressure distribution like
When you have a
200 300.
wave, let's say,
Hmm.
so sound waves, right? So they're
Yeah.
so in acoustics, you might get a wave of such frequency that at
Hmm.
each grid point the pressure changes like this. And
Okay. So yeah. Oh, okay. So if I have some such kind of flow,
hmm,
like where the pressure distribution is like 100,
yeah,
then 200, then again 100,
hmm,
then based on pressure gradient,
hmm,
the flow will be matlab, I mean to say the flow is away from P point. If I am at P
yeah,
point,
exactly.
then 100 both side 100, so it is away from. So basically where we get this velocity, like it is very complicated velocity
So,
because.
so the perfect example for this is acoustic sound waves. So right. So there is this peak and trough of pressure, and you
Hmm.
get peak and trough of velocities a little bit shifted. So zoom in over here. So let's say pressure is, pressure nodes are over here at hundreds, and the anti-nodes are at 200. Then I will get the nodes of velocity at small e and small w, and the uh, the altering points, which is at the capital P, capital W, capital E. There will be the velocity anti-nodes
Yeah, but this is at one moment.
at
The
one moment.
next
It's a
moment.
dynamically changing problem.
Yeah, but next moment, I mean to say, means next moment the pressure will gradient will change, so
Will change, yeah. But if you are
wave will
using
move forward.
but if you are using a collocated grid, then it will give me zero velocity everywhere because it cannot understand that there is a
Ah,
velocity.
yeah, okay,
So
okay,
it works as
yeah,
zero to
that,
it.
okay, yeah, yeah, yeah. There the decoupling is there,
The
so that's
decoupling is there.
okay, okay, that's understood.
This is a
Okay, so
very specific problem, but then again, the collocated grid is not really super interesting.
okay, so EMW market centers. And this is the oscillatory problem. Like it was told that there are some oscillatory problem. This is the oscillatory problem. This checkerboard.
No, no. The oscillatory problem there is oscillations in the solution. The solution will not converge, but will keep oscillating from some average value. You won't get a converged solution. It will just keep jumping here and there.
Okay, so like it was told that because of this decoupling problem, we can have oscillatory solutions. Like
Yeah, that's about the numerical solution. Oscillations in the convergence.
okay, velocities are known in standard. Okay, standard. Can you move to the next one?
Yep.
Yeah. So here, like this, the very first equation continuity, del u by del x. So uh, this diagram, can you? Yeah. So here del u by del x. So I mean, I was in this cell. So I use up and minus uw. So I basically like when I'm trying to find velocity, this del u by del x,
Hmm,
then p is my point.
hmm,
So I use up minus uw, right? But when I am at pressure,
hmm.
then I go to the phase.
Hmm.
I basically mean to say that when you're calculating this del u by del x in the very first equation of continuity, then my primary cell is this main cell P,
Hmm.
and when I am calculating pressure gradient del P by del x, then my main cell is phase.
The pressure is pressure cell.
Uh, uh, no, pressure shall not at Vp, because we write Pe minus Pp. So we are at phase for calculating pressure
Yeah,
gradient.
yeah, exactly. So then also we are using the grade for U itself. When we are calculating the uh, X gradient of pressure, then our
Hmm.
cell is this cell, the one where P is at center.
Okay, so basically our cell is UP only.
Yeah, so
VP, UP only. Yeah, this
yeah,
cell.
so if I just zoom in, this is our cell where UP when I'm calculating, then I need,
Hmm.
pressure on the right hand side and on the left hand side, and I take a difference between these two. So it's more physical. You can understand that in this cell, what is the pressure here, what is the pressure here, and that difference is going to drive the flow.
Yeah, but
Similarly,
okay, that
similarly,
okay,
when we are
but
interested in 1 second. So similarly, when we are trying to solve for dp, that is the y momentum equation, then this will be our cell. Then we will calculate the pressure difference between pn and p.
okay, so basically for this velocity, these are the pressure we are going to use. Basically, in
Yes.
this is for okay. But for the velocity thing, del u by del x in the first equation,
Hmm.
we have written V UP minus
Yeah. So
UW.
yeah. So then our uh, grid is this one of p, pressure p at point p. So then this is our control volume. You can see my
Oh,
cursor, right? So
understand.
what
Yeah,
goes
yeah,
in
yeah.
through the
Understood.
left side, what goes out through the right side, and what goes in through the what goes out through the top, that should all match up.
Okay, so can I think it in this way? Because there is a pressure gradient, there is a velocity. So I write pressure gradient in terms of velocity. In the same way, there is velocity difference, so there is a pressure.
Exactly.
So, so then when I'm writing for this del u by del x,
Hmm.
then I will use this thing,
Yeah, the
which is
pressure,
resulting in pressure.
pressure itself.
Okay, and when I'm going for pressure gradient,
Hmm.
then I will see that it is creating some velocity.
Exactly. So that is much more physical, right?
Okay, because I am not able to decide which cell
Hmm.
I
So
should
the
be.
logic is that get it now, right?
Yeah, so this is the logic. I am just not manipulating it. It is the
Yeah,
logic.
yeah, yeah.
Like it is written in books like logic, or just we are assuming it to have this equation.
Many things are, if you read some good books, then it might be there.
Okay. Okay, but the logic is same, because for the first equation continuity del u by del x,
Hmm.
like you, or I am thinking like because I am thinking that maybe they have used an backward
No,
scheme.
yeah,
That's
so
why it was
there
written.
is a box which looks like this. Sorry. So this is the box. There are
Hmm.
velocities coming in and going out through this box. They should
Hmm.
add up to zero for an incompressible. That's the main logic.
Okay, and for pressure, I need to be on phase that.
So why is that? Because dopey dou x and dopey dou I, these are all used in the momentum equations when we are solving for u and v. So dopey dou x shows up in the u equation. That's why we use the u cell as well. Where
Okay.
here our question is, what is the pressure difference driving the
Oh, okay. Yeah, X momentum equation.
yeah,
So that, all right.
and the similarly for v also,
Y.
dopey dou I is what is creating v. So then
Hmm.
also we need to look at the v cell where we have v at the center, and there is a pressure
Hmm.
up top and in bottom. What is the pressure difference driving?
Okay. Okay. Thank you. Now, next, can you move to the next lecture?
Next lecture.
Yeah. Okay,
Roland,
so
can you see my screen?
yeah, no, no, no. Just a minute. I need to find out because it is very complex. So I need to think a little bit where I'm asking. Just a minute.
Hmm.
Yeah, in the very first slide itself, like uh,
This one or
this no, no, this slide only where you are. Okay. So now here I again in the convection term
hmm.
I write UP. That's fine.
Hmm.
That's I am writing UP. But when I am writing del U by del X,
Hmm.
then again I have to okay now I use UE minus UW.
Central difference.
Yeah, but by this logic we have just discussed, it should be UP minus UW.
Then it becomes what, backward difference, right? You lose out on order of accuracy.
No, no, we have just discussed that. That's what I'm saying that we are using backward difference. But you said that the
Yeah.
physically we need to look that.
Mhm. So
Uh,
pressure is like this, yeah, the pressure difference.
okay. No.
But for velocities, if I want to, find out what is the velocity gradient over here at this point, can you see my cursor?
Yeah.
So we have two options. One is either do backward or forward difference. That will give me order delta x accuracy, or I can do central difference. That will give me delta x square accuracy. So I make the choice of doing a central difference.
Okay. So like
Hmm.
in the previous lecture, there for pressure we can think in this way, but
Yeah,
this thing is like there we have used backward scheme
I
for del U by
understand.
del
So
X.
it seems the same thing back again, but for velocity we do this, but pressure we can find out this way, where we're using delta x as the grid resolution.
Okay. So.
So there are other benefits of doing this, like pressure velocity coupling is ensured and all that.
Hmm.
So this is not
Okay.
that big a problem.
Like for P we use PE minus PP.
Hmm.
So
Why?
PP is where
Yeah,
like in this equation pressure
we just
gradient, huh?
discussed. Why do we do this?
Minus PP. Okay, so we are in the U cell, UP cell,
Exactly. So we are trying to solve for u. So PE minus PP will give me UP.
but it is first order accurate then. But it is here it is written that it
First
is
order
second order.
accurate, but it's velocity pressure coupled. The other option for collocated rate would have been to take PW and PE.
No, after pressure gradient, we have this pressure gradient term. It was written that it is order of accuracy is x square, delta x square. But it is not central differencing. We have just simply.
Yeah, it's sort of central difference because see, there is a pressure over here as well, where E is there.
Hmm.
So it's sort of I'm taking central difference between that. That's
Okay,
why.
we are
We're
taking
not
okay.
explicitly solving for or calculating what the pressure is,
Hmm.
but it's sort of like we're taking central process.
Okay, okay. Can you? Okay. So one thing is like this. If I need to see this, so this is also central differencing UE minus UW control delta x, and this is also central differencing, and I am in this cell only. So for this, because pressure velocity is known only at those points, so
Hmm.
that's why I have written this, and
Interpoint.
pressure is known at this point, so I wrote this. Okay, yeah. To some extent I understand. Okay, now, so U gradient in both the lectures. Location of U and temporal. Yeah, can you move to the next slide? Uh, okay, yeah. Now here we it was told that we are using forward time central space,
Hmm.
right? Now forward time is explicit in nature,
Yeah.
but then why we wrote this pressure term in n plus one? It should be n.
Yeah, so that it remains coupled. So at n plus 1, whatever pressure difference is there, that is the one driving the velocity at n plus 1 as well.
Yeah, but we changed the scheme then.
Yeah, so scheme, see, because earlier, whenever we learned forward time, central space, and all that, we had only one variable which we were solving for, right? It would be some phi, dou phi dou t plus dou 2 phi dou x square equal to 0. Here we
Okay.
have pressure and velocity both. So if sir is telling that this is FTCS, this is FTCS for U.
Okay, so whatever term u I used, that I will take for nth only,
Yeah,
and n time step. I
yeah.
mean, but pressure is driving. Yeah, logically it is correct, but mathematically, like we are randomly putting
I agree with
anything.
you. You can take it up with professor and have a debate with him.
Okay, but
But
actually his
then
last
again,
session is over.
this is what the Mac scheme does, and the way Mac scheme was developed and the research behind it, we are not really going into that. And I really
Okay,
can't explain what's the exact way in which we arrived at this, but
but the only logic you told is correct,
yeah,
because the pressure is driving that velocity. That's why it should be n plus one level. But mathematically, I should say that I must use the previous data.
yeah,
Okay. That I wrote also because his sessions are over, so maybe I write. But in books it is there. Have you found anything like in
I
books?
think so. I can't remember exactly right now.
Like, is there any explanation why we are using p n plus one in books?
I can't remember.
Okay, okay, okay. But
But
it is a thing. Like, it is not a random
yeah,
doubt. It is.
yeah. It didn't come out of thin air for sure.
Only solved.
Anyway, let's get.
Yeah. So, are there any other methods also like map algorithm?
Yeah, there should be. I can't remember any now, but see, first of all, finite difference method is rarely used for solving Navier-Stokes. We, 99% or all, 99%, but like 80% is using Dalal method, and maybe rest is using finite element method. Finite difference
Okay.
method rarely is used for solving Navier-Stokes. We learn it because it's easy to, dip our toes into this computational fluid mechanics.
Okay. But there are very less, like only two lectures for FVM. It is sufficient to go to that level that we can solve.
You can follow up some other courses. This course is, an introduction to.
Okay. Okay. And this the assumption in this, it was told that in Mac algorithm, we made this assumption that all the pressure nearby is zero.
Yeah.
So how we come up? with this.
Out of thin air. I just say, man, this is too complicated to solve, so I will
Hmm.
ignore this. But the only thing that comes and saves us is that we do this iteration. First time we do this, we get an incorrect solution, but it is near to the
Yeah.
actual solution. So we keep doing that again and again and again, and so that we keep going closer and closer to the actual solution.
Okay.
So in
Okay. But,
finite volume method also you will learn about simple C, simple R algorithms. There also you will see a similar philosophy where neighboring correction terms are just thrown to the dustbin, that I don't care right now.
but it doesn't matter. Like even
Yeah,
instead of zero, I take 5 or 10 or anything.
you could.
At the end, it is going to update.
No, you could do that, but then again, when you're iterating again, then you will again, sort
Hmm.
of get rid of those errors which you introduced. So see, it's not that we are not solving for the neighboring points, because uh, this PP is just for one point, and we do this for every single point, right? So the
Yeah.
neighbors of what you had ignored earlier, you solve for those neighbors in the next.
Yeah. That's why I'm saying that if we want to finally going to update this equation, no matter we take 0, 5, 10, any
Yeah,
number.
yeah.
Okay. So that's fine now. Okay. So yeah, can you move to yeah, this last equation ppn plus 1, this ppn
Yeah.
and then p correction factor. So uh, like we have found out pp means correction factor we have found out.
Mm.
ppn is from previous iteration
Yeah.
and ppn plus 1 is like the current
The one
like
that
current
we
iteration.
solve.
Yeah, and when it is converged, it is this correction vector is 0, so it is
Yeah.
equals. Yeah, this is I'm getting right.
Yeah.
Okay. Okay. Then it is okay. Now, yeah, like in this over relaxation factor, this
Mm.
it was told that by trial and error, we try to find out this over. Like I'm not telling you to go in the details, but can you give some glimpse that how this over relaxation factor is considered and how we calculate it?
So see, the main funda behind over relaxation factor is that I have a solution, and I'm starting from some point and I'm stepwise going towards that. The steps are
Yeah.
that correction curve, the dash. So
Okay.
if I multiply the one step by some amount, so I'm
Hmm.
getting more closer to the correct solution at each step. So this speeds up the solution. Now let's say I take too big over relaxation factor. So my difference would have been this. I cross it and go over. So in that case, I will keep oscillating about main solution without ever reaching correct solution. So that's why I can't take too big an over relaxation factor. But then again, I want to take greater than one so that it actually speeds up my process.
Okay, but okay, okay. Now I understand. Kind of, we are increasing the time step.
So how much we move in one time step, that we are increasing. Yeah.
Okay, yeah, and we are just we will cross check it that we will be near to the solution. That's
Yeah. So that there
okay.
is a optimal over relaxation factor for every case, and uh, for the simple known cases, maybe there's a formula or some empirical guidance to what the optimal over relaxation factor could be. But for very specific cases, you have to find out through trial and error what's the optimal.
Okay, fine.
There is no way to entirely say that
Okay,
1.56 would be the optimal over relaxation factor.
okay. Can you move to the next one? Yeah, here in this first thing we initialize this UN, VN, PN,
Yeah,
right?
yeah.
So to initialize, we take 0 everywhere.
It depends. There are many. So, have you used any CFD software by any chance, like Fluent or OpenFOAM?
Yeah, Fluent and I have used and
You've used Fluent, right? So, in Fluent, when you go to initialize, you'll see there are different options to initialize, right?
yeah.
So, taking everything zero is, the simplest way to initialize. There are other more complicated ways to do that as well. Like, let's say, for example, um, you're trying to solve for flow through a parallel plate,
Yeah.
right? So you sort of have an idea that there will be a flow in the parallel plate, so through the parallel plate. So taking zero is sort of useless, right? So you can guess that whatever u I am giving in the inlet, let's initialize with that u itself in the whole plate. Then during solution, the flow will slow down near the values and it will correct to the actual solution. But giving
Okay.
some velocity, when I know that there will be a velocity, it's not that it will be zero everywhere. So in that case, you can make better guesses of initialization. In that way, the number of iterations you need to get to the solution, you can reduce that.
Okay, but if we are not getting any idea, then we can start by zero.
Yeah, zero is as good as anything.
Okay, and then about this steps about updating this boundary values, boundary conditions.
Hmm.
I don't understand because boundary condition is something which is fixed and it actually decide the our
For
solution.
for Dirichlet, it's fixed, but let's say when you have that outflow kind of condition where dou u dou x has to be zero, so u in the internal field changes. So u at the boundary
Okay,
also you have to update, right? So for my
understood.
drawing,
So only for Newman is we need this
only for Dirichlet it's
updating.
fixed. If it is not Dirichlet, then we'll have to
Yeah, that's what I'm saying. That for his Norman boundary
correct,
condition that we need to update this boundary values.
correct.
Okay, 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 okay. And fine PN. Okay. Yeah. So okay. Yeah, these are the doubts.
Okay,
uh, yeah. Thank you very much. And there are some other things also, but we will discuss in the next session maybe.
sure, absolutely.
Yeah.
Okay,
Yeah, I just want to, like, if I can discuss one thing, like yeah, I think you belong from the this computational field only. Yes, computational fluid dynamics.
sort of, yeah.
Sort of. I mean to say that is like why I'm asking this because like if we are dealing in CFD, then do we have the opportunity also to go through other fields, or we need to stick to the only fluid mechanics, only heat transfer?
Absolutely not. Absolutely. I'll tell you about myself itself. Like, I am
Yeah.
still pretty young and very new to this field,
Yeah.
but so far, I'll tell you what I've done. So during my UG, I did a project on, modeling hydrogen combustion. For that, I used ANSYS Fluent. Okay. So
Okay.
combustion is one area. Then during an internship at IIT Kanpur, I worked on modeling sprays. So sprays, right? So maybe
Yeah.
perfume spray or fuel spray in an engine. So where bulk liquid is
Mm.
broken up into droplets. That can
Yeah.
be done using CFD. All right. So then after graduating,
Yeah.
then I joined IIT Madras for my PhD. So here I work on aerosol deposition in the lung. So whatever
Yeah.
particles you inhale, it could be medicine inhalers or it could be COVID containing droplets as well. So how do they flow inside our respiratory system and get deposited? Once again, I used a little bit of CFD for that.
Okay.
Then
But it
currently,
is. Yeah.
let
Yeah.
me
Yeah.
finish.
Yeah.
Currently, I'm doing an internship at GE Aerospace. So here I'm
Oh,
working on additive manufacturing and the thermal aspects of it. So for this also we are using some modeling ideas about how heat will flow uh, in a 3D printing uh, modularity. So You can see like lungs, combustion, manufacturing. I've already covered three, and there are tons of examples where this can be applied. So you're not really
Okay.
stuck. You are anything but stuck. You confused by the different options available there.
Oh, but the primary equation and the fields are same, like
Exactly. So
fluid.
everything is do phi do t, do
Yeah,
phi do
yeah.
x, do 2 phi do x2, and all that.
Okay, but the applications are
Yeah,
different.
the phis and the x's and the y's they keep changing, but
Okay.
the main methods remain the same.
Okay, I will discuss about this in maybe more in the
Yeah, yeah,
coming lectures.
absolutely,
Yeah,
absolutely.
about sessions. Okay. Okay.
Okay,
Okay. Thank you very
okay.
much.
Bye.
Thank
Take care.
you.
Good night.
Okay, bye. Good night.